Welcome for those of you who are joining us today for the first time. My name is Rebecca Medlin. I'm a member of the research staff at the Institute for Defense Analyses and one of the 2020 workshop organizers. So those unfamiliar with DataWorks, we're a workshop designed to build a community around rigorous statistical approaches to the complex problems that we face in DoD, NASA, and the national labs. The organizing of this event is a joint effort between IDA, DOT&E, NASA, and the American Statistical Association's section on statistics in defense and national security. Before we get started, just a few quick items to note. All of the materials are available on the DataWorks website. So if you go to the webinar agenda and look at today's meeting information, you'll find each speaker's slides if you want to follow along or save those for later. So I'd like to thank our three speakers for volunteering to speak in today's session. So they're going to talk on the topics of both test design and validation related to some of our DoD weapon systems. Our first speaker, First Lieutenant Quinn Stank, is the lead analyst for the Air Force Operational Test and Evaluation Center Detachment 5 at the Everett, Washington location. Quinn serves as the advisor to the Operational Test and Evaluation team for the KC-46. He originally comes from Knoxville, Tennessee, and received his commission as a second lieutenant upon graduation from the U.S. Air Force Academy in 2016. So Quinn, I will turn things over to you.
Thank you. And let me share my screen real quick. All right, can everyone see that?
Yep, we can see it.
Great. So good morning. My name is Quinn Stank. I am the lead analyst from the KC-46, on the KC-46 Alpha for AFOTEC Detachment 5. Basically what that means is I control the data sort of from cradle to grave. I work with the design of experiments. I work with the survey creation. I work with the scheduling and the test point planning. I work with report writing. I work with analysis, data engineering, kind of the whole spectrum of the data on the KC-46 Alpha is my wheelhouse. And so if you've seen a report from us or seen something in the news, odds are good that either me or someone on the team that I work with has something to do with the data that you're seeing. So this is a brief based on adaptive relevant testing, which is the AFOTEC challenge that we've kind of taken on in order to increase the performance and the capability that we're delivering at a faster pace compared to historical testing techniques from the past. And so that's what this brief is about, is our kind of culture change in the way that we've applied it to the KC-46 Alpha to deliver capability to the warfighter. So the overview is first I'm going to talk about kind of what ART is, what adaptive relevant testing is. I'm going to give you an overview of the KC-46 Alpha and the goals of the jet and the weapon system, so you can kind of have some background, and then we're going to look at how we apply ART to the KC-46 along the acquisitions triangle of schedule, performance, and cost. And then I'm going to give you some real-time examples that we've used and seen in the program, or you might have read about, and kind of my perspective on that. So the purpose of this brief is to go into detail about adaptive relevant testing and talk about how the KC-46 team has used these AFOTEC principles in order to deliver capability faster to the warfighter at a cheaper, more efficient way compared to traditional methods. And the traditional method that I'm talking about here is, essentially black box initial operational test and evaluation, where we wait till everything's ready. We go to test for 6 months. No one hears anything. No one gets any data until it's all finished and published in a final report. And then fixes can be made. So that's when I'm talking about that traditional method. That's how I'm saying we're trying to go away from that. And we're trying to use ART principles to do that. So to start with, you're going to hear me talk a lot about the DT mindset and the OT mindset a lot. So just kind of a blanket statement. Developmental test, in my opinion, from an operational tester is much more focused in the weeds kind of, and maybe not in the weeds, but they're focused on smaller minutia things. They're looking at the capability production document. They're doing verification. They're saying, does the boom fuel flow meet the criteria that we set about when we wanted to build this weapon system? Whereas the operational test mindset is much more of an operator and aircrew, a mission focused mindset where we're validating and we're saying, hey, can we perform the mission? Can we, rather than what was the fuel flow on the boom, were we able to give fuel in an operationally realistic time frame in order to complete the mission? So you're going to hear me talk a lot about the DT versus OT mindset during this brief, and that's kind of what I mean. So to begin, AFOTEC ART is based off of the 2018 National Defense Strategy from General Mattis, where he wanted acquisition programs to deliver performance at the speed of relevance. And so you're going to hear me talking about delivering capability. We want to do it faster and smarter at the speed of relevance, as you see on this left-hand chart with this triangle. And we're going to do it under the acquisitions framework of kind of the acquisitions triangle of cost, schedule, and performance. So to deliver speed of relevance with high performance, we want to discover problems early on that left-hand side. If you can see my mouse here, I'll kind of use that as my laser pointer. So we want to discover problems early. By doing that, we're going to allow us to fix problems earlier, which means we're going to deliver better performance to the warfighter with the combat capability in the middle. On the right-hand side is kind of our cost side. So we're going to reduce costs. And the way we want to reduce costs is we want to find these problems early. It's a lot easier or a lot cheaper to fix issues when, say, we only have 3 test aircraft that we need to fix a problem on compared to a fleet of 180. So you probably have seen in the news that, the KC-46 is replacing the boom or replacing the vision system. Programmatically, it's way cheaper to fix 20 aircraft than 180 aircraft. And so that's kind of where the cost aspect comes into play. And then the bottom triangle is the schedule part of the acquisitions triangle. We want to test earlier, faster, and smarter. We want to get the weapon system to the field faster, and we want to do it at a lower cost with higher performance compared to these traditional methods that we've been using. And so that's where that combat capability comes in the middle, where all 3 come together to give the best capability to the warfighter. So the AFOTEC's response to this national defense strategy is ART. And there are 6 key principles to ART. And I've kind of touched on a lot of them and through talking about the triangle, but we want early OT involvement. We want to push that schedule to the left. We want to test smart and tailor the situation. We want to be adaptive. Number 6, 2 and 6 kind of go together, that we can be flexible and smart in order to get us continuous feedback and streamline our processes and then integrate and combine our tests. So you can see how everything kind of goes together. But ART is really AFOTEC. The thing I want to put on is ART is AFOTEC's goal for answering the national defense strategy of delivering capability at the speed of relevance. So talking about the KC-46 now, just kind of a brief overview. This picture here on the right-hand side is the concept of operations for the KC-46. So every acquisitions program in the Air Force gets one of these. And basically what this is it's an overview of what we want the jet to do in picture form. So we want it to do aerial refueling. We want it to be like a KC-135 on the bottom you'll see, but we want it to be an enhanced version of that. We want to do airlift. We want to have cargo and passenger airlift, and we want to do aeromedical evacuation as well. The key here that I really want to foot stomp that's going to bring AMC and bring the tanker community into the 21st century is all of the lightning bolts on the screen. It's our command and control aspect, our situational awareness, that basically we want to have a pseudo AWACS mission set with also a KC-135 mission set. And that's what really separates the KC-46 and brings this enhanced mission concept, is that it's a tanker. It does everything legacy tankers do, but it also has all these new situational awareness and C2 capabilities that it can share not only with the Air Force, but joint as well with the Army, Navy, and other friendly military partners. So that's kind of the goal of the 46, is that it's a tanker plus. And that's coming from the C2 aspect of it. Going into our test design a little bit, so we use standard DOE methodology. We have 5 critical operational issues that I'm going to talk to here in a little bit, but each one of those 5 COIs are their own experiment. And so each experiment has an 80% power level with a signal noise ratio of 1.5. Pretty standard stuff. We have roughly 4,500 data points across 700 test events, and each of those 5 experiments has their own factors and levels and things that we're looking at in order to, make sure that our conclusions are sound, but also answer the questions of what this weapon system is supposed to accomplish. Flight tests are a primary methodology. AFOTEC headquarters approves our final test plan, but we also have DOT&E approval of our technical adequacy, and we work with advisors from IDA to help us with that as well. So going more into our test methodology. So our test is split in half almost. You have effectiveness and suitability. And so effectiveness you can think of as operators. It's air crew. And so this is the guys in the jet. This is the AR aspect. As you can see, our 3 critical operational issues, or COIs on the left, are AR, air refueling, airlift operations, so cargo and passenger, as well as aeromedical evacuation. So when we're testing the effectiveness of the aircraft, these are the mission sets that we're talking about. We have 2 main ways of doing that. We have ground test and we have flight test. Primary means, once again, is flight test, but it's not just AR. We're not just looking at fuel. We're looking at everything on the jet and how that enhances the mission. So does the lavatory work? You know, there's going to be limitations to the aircraft if you can only be aloft for a certain amount of time because the lavatory capacity is low or something like that. Cargo and passenger operations, how do we load the jet? What is the cargo floor like? And then aeromedical evacuation operations as well. You know, how much water can we hold for patients? How much oxygen does the jet hold? As well as the ground stuff that, above, such as the alert launch and things like that. So that's kind of what we're looking at when I say effectiveness, is that this operator mindset, this air crew focused perspective. On the next slide, we talk about suitability here. And so this is maintenance. So suitability has two main critical operational issues, which once again are their own separate test designs. And we have, can the KC-46 be generated to meet mission tasking? So what that means is basically, can we perform maintenance on the aircraft to have it ready when we need it? And then is it logistically supportable? So if the KC-46 breaks down in Hawaii, or if it breaks down in Germany, do we have the supply chain and the parts on hand in order to fix it, not only effectively, but efficiently in time, with relatively low time? And so the primary means of that is ground evaluations. We have maintenance experts who are out there and they're running through checklists, they're running through publications, the interactive electronic technical manuals, and they're watching maintenance members perform maintenance tasks and they're grading the effectiveness of that. You know, basically, can I perform a maintenance task? Can I get this aircraft ready to fly with the products that we have? And then we also have analysis. If you're familiar with maintenance at all, we use GEO81 data, and we can get, you know, aircraft reliability, maintainability, availability. We use these typical maintenance metrics along with the sustainability and the supply chain in order to rate both of these critical operational issues. So now that we kind of have a background on the KC-46, we kind of have a background about ART. I'm sorry I went quick through it, but there's a lot of examples at the end that I want to talk about more in depth. We can kind of talk about the acquisitions triangle here and how we've applied it to the KC-46 program with this methodology and this test framework. So the first thing we want to do is we want to test systems when they're ready. So we want to look at our schedule. So the KC-46 is a great example of testing systems when they're ready, just based off of FAA certifications. So the aircraft has, or the DoD has 17 different receiver aircraft that they would like the KC-46 to be able to refuel. When we started operational tests, there were 3 that were certified by the FAA to be able to test. We had the F-16, the C-17, and the KC-46. When I talk about a historical IOT&E, we would have waited until all 17 receivers had been certified by the FAA to test, which still hasn't even occurred. So we wouldn't have even started testing yet. But because we started early, we were able to test those 3 receivers. While we were testing those receivers, we've gotten more certifications along the way. We're still not at all 17, but it's been allowing us to test while we can and to move that schedule to the left. So as you can see, we had 22% of our test points completed before our official start of operational test. And that's because we're pushing that schedule left. We're trying to ID issues early and we're trying to lower costs because of that. Some of the limitations of this, the biggest thing that we found is the contract type. So the contract type in the KC-46 is a firm fixed price contract, which means it's really difficult for us to make any changes when we have new discoveries or even to get access to things that we would like to see. So when Boeing was doing contractor testing, we missed out on a lot of data because we couldn't be there to be a part of it because it wasn't written into the contract. Another issue is that some systems simply aren't ready. You know, kind of like I talked about, by testing when systems are ready, other systems might not be ready. And so it isn't the most efficient in terms of test points sometimes because of that, because you can't test everything. And then lastly, something that we really didn't think about is the increased demand on personnel. So the first slide of this brief was a picture of the first day of tests. And I was actually just looking at it when I was prepping for this brief yesterday. And there's 11 people in that slide. And 6 of them will be gone by the end of this summer. So we're losing a lot of our knowledge on the test. There's just a lot more demand for people longer than expected compared to a historical IOT that lasts 6 months. Everyone's going to be there the whole time. And you know, we're going to lose basically half our team, if not our whole team, in the next 6 months to a year by the time everyone PCSs, and just kind of the nature of the military. So there's some definitely limitations on the way that things work by pushing things left, is that you're losing a lot of your expertise throughout the test. Now I want to talk about identifying issues early. So this is the performance aspect of things. So by testing things incrementally, by testing them earlier, we're identifying issues earlier. The buzzword that I always hear is we want to categorize the operational envelope of this aircraft. Whether it goes good or bad, we want to let the warfighter know what they have. And so, the lessons we learned from the C-17, while not a one-to-one trade to a B-52 that we might get the cert for 6 months later, the aircrew is still training with the C-17. They're still learning about the system. We're still getting data on the system, and we can still provide those lessons learned to the B-52 when the time comes, so that the warfighter is more prepared in order to do their job. Another big thing that I want to foot stomp is integrated testing. So developmental tests, they have their own DT test. We have our own OT test. And we really want to kind of blur the lines of those tests and bring them in together. We want to work with DT more often. And the KC-46 has, and I have an example later on to talk about how we worked with DT and how early OT involvement with DT is beneficial for everyone. So once again, some of the limitations are that we can have rediscovery of DT data. So this is mitigated by effective integrated testing, but the Tactical Situational Awareness System is a SA system. It's it's basically the hub for all of the C2 systems, or a lot of the C2 systems on the KC-46 Alpha. And we've learned that there's a lot of issues with the TSAS and the interface with the aircrew. We found that out, and then we talked to the DT guys, and they had the same issues. And so we basically doubled up on testing. When if we had effective IT with TSAS, we would have been able to know that prior to even testing, and we wouldn't have wasted range time. In addition, training and support may not be representative in an operational unit. So in order for us to call it operational test, we have to have an operationally representative test scenario, essentially. We need to have operators. We can't have test pilots. We can't have test booms. We need to have, guys from the line, maintainers from the line that are going to do this in the real world. And so you can mitigate this with effective integrated testing, but one of our biggest issues that we've run into is a lot of these C2 systems, to keep this example going, are not on legacy tankers. And so when we're finding problems, it's really hard to attribute it and to figure out what causes the problem, because we're pushing so far to the left and we're trying to get there as early as possible. Is it a training issue? Was it an aircrew issue? Did they just have a bad day? Or is it actually that the system has that fault and there's a problem with the way that it interfaces with the KC-46? So that's one of the biggest limitations, especially as an analyst, that I've seen is, just because it's bad data doesn't mean it's bad data, but how do we attribute that bad data? Is it because the aircrew just didn't know, or is there actually a fault with the system? And then lastly, we're trying to reduce costs through our optimized testing. So I kind of talked about it a little bit. We're looking at programmatic costs here. We want to decrease the long-term costs by finding problems early, fixing them early when we only have a few aircraft, and that way we don't have to, send 180 aircraft to depot to get fixed over 5 years. In addition, we want to be on the figurative knife's edge of our testing. As a lot of the people in this community know, sometimes usually more data is better, especially when it comes to power and statistical rigor and things like that. And we want to be kind of on that knife's edge where we want to get the signal to noise ratio, the power that we need, but we don't want to do it at a waste of testing, essentially, in order just to get something done to get it done and to do more. So some of the limitations is that, especially with the figurative knife's edge of testing, from my standpoint that I've had trouble with, is explaining to people why we need to do a 4th or a 5th or a 6th test when, the operators see that mission operational test mindset that, hey, I've already done it 3 times. I know the outcome. Why do we have to repeat this? And that's really hard from an analyst standpoint to talk about how the statistical power and confidence matter and how we need to increase our sample size and things like that. In addition, so the long-term cost of the program might be lower, but the teams are going to be in place longer, and you're going to increase more short-term costs in terms of TDYs and things like that. And then lastly, if we're not efficient, if we don't have good integrated testing, obviously retesting and rediscovery of test points isn't the most efficient. It's going to increase your costs. So I want to talk about some examples now. And this slide was supposed to build, but I don't know if you guys read about it. It was pretty big. Obviously on the KC-46 team, it was huge. That there was a Cat 1 emergency deficiency report published due to the cargo floor unlocking during flight. And so here's some news articles that we're supposed to build. On this next slide, we go into detail, and you can see the news articles at the top. There's something I pulled off of Google from a quick search. So if you want to find out more, you can read those as well. But basically the background is that the KC-46, one of our critical operational issues is that we want to be able to do airlift and carry cargo and passengers. So the cargo floor of the KC-46 has these different locks and latches in order to secure pallets onto it. And so they're equipped with a quick release that should be easy. You know, sometimes you're moving thousands of pounds of gear and people, and you want something that's quick and easy to hook into the floor, lock, and be safe. The quick release has a tactile indication of lock, and it clicks when the user turns it. And I'll show you a picture on the next slide. The issue that we found is that these locks that are securing the pallets to the floor are actually coming unlocked from the floor during flight, or were coming unlocked from the floor during flight. And during, technically prior to official OT start, we had a test boom find this out on a test flight. So, you know, we were there early, we were testing these capabilities, and by being there early, we were able to ID an issue early and, you know, put a deficiency report out to get it fixed. So on this next slide, you can see on top is the old, and hopefully you guys can see my mouse. I don't see my mouse right now. There it is. And so you can see, so this lever and this latch is what you swing to lock this pallet lock onto the floor. And per the Boeing publications, if any red sticker is showing, then that latch is unlocked. These also wobble and tend to move. And so what this means is that this big red latch will lock and hold the pallet into place, but it's actually not connected to anything, so that pallet can slide. And obviously, you know, CGO or center of gravity considerations are huge here. Any type of shifting of cargo during flight is a bad thing. It can crush people, crush equipment, put a hole in the aircraft, as well as, you know, potentially affect the center of gravity of the aircraft and cause it to crash. So pretty major issue here. By us coming early and being out there and discovering this and writing this deficiency report, we were able to get a fix from Boeing. And as you can see here, the fix is really simple. It's just a button that you push down when you lock it. So when you want to unlock it, you push the button and turn it left. And when you lock it, you push the button and turn it right. And it just holds that latch into place. So it was a pretty simple fix engineering wise, but it had major outcomes on the aircraft. And so by us being there early, testing early, identifying this deficiency, reporting it, we were able to actually get a fix within 3 months, when if we had done a traditional IOT&E, it would have taken 6 months for anyone even to find out that it happened. And then in addition to that, we were testing throughout the whole time the fix was being developed. We weren't flying with cargo because that was unsafe, but we were still able to do AR testing. We were still able to do, you know, TSAS comms testing, all this other stuff that we can deliver to the warfighter incrementally, even though we couldn't give them cargo. And then another example about kind of really what to me brings the operational test mindset to light is the aircraft performance tool. So in the acquisitions framework, we, as OT, we do operational assessments throughout developmental testing. And so in May of 2016, TOLD, which is takeoff and landing data, was provided using a Boeing FAA certified dispatcher. And so why that's significant is that takeoff and landing data is required in terms of safety on flight for takeoff of every aircraft. If you have an engine failure, if you have any type of emergency, you only have so much runway left that you can stop in order to be safe, essentially. So what the TOLD does is it gives you those speeds and those times, essentially, where you can say, hey, I have enough runway left to stop, or if I have an emergency, I have to go into the air and I have to figure out in the air. And so it's really a safety of flight issue to not have correct TOLD and not to have accurate TOLD. And so for Boeing, it wasn't an issue because they just used their dispatchers and they just printed it off and they gave it to the test pilots and they went and flew. But from an operator mindset, from a mission-oriented mindset, that's a huge issue because the Air Force operates all over the world. We don't have Boeing dispatchers to print us off TOLD data, and it's required essentially for this aircraft to do any of its missions. So what happened is in our operational assessment too, the OT folks wrote up that there's a major operational deficiency of the aircraft because it cannot calculate its own TOLD. And as a result of that, no OT testing was held back from it. No DT testing was held back from it. And in January of 2019, when the first KC-46 was delivered, it calculated its own TOLD using APT. So that was a big win from our perspective, is that we brought that operational test mindset to DT. We worked with our integrated testing and we were able to fix something before it ever was even an issue. So lessons learned. Sorry, I went kind of fast. There's just a lot of information, but the biggest lessons learned that I want to foot stomp are integrated testing is critical to everything. If we want art, if we want to deliver at the speed of relevance, we need to remove this OT versus DT mindset. We need to test. It needs to be just everyone together, everyone working together. The DT mindset is critical in order to get a working weapon system. The OT mindset is critical to get a working weapon system, and we need to work together. and just test aircraft rather than be separate and different. In addition, no system is 100% ready. We have to test what is available. Nothing's on a jet aircraft like the KC-46. There's, it's a system of systems. There's thousands of systems on it, millions of parts. Nothing is always going to be 100% ready. So you have to test what is available when you can. And so the cargo example is a great point of this, where we were able to test for 3 months when a historical test would have shut down. Next, big thing is contract type. When you're working on these weapon systems and things like that, the type of contract you have can be severely limiting until the contractor allows you to look at it. And so the firm fixed price contract was a huge limiter on the KC-46. And lastly, we want to communicate our results at an actionable level. So nothing that we discovered, nothing that we found would have mattered if we communicated it a year from now or 6 months from then even. The fact that we do daily sit reps with shareholders, we have periodic reports which come out every 3 months. What that does is it gives you basically a snapshot in time of where the KC-46 is, and it allows decision makers and shareholders to have accurate data on the jet in order to fix what's wrong and plan for it in the future. So like I said, sorry, that was pretty fast, but I had a lot of information. And if anyone has any questions, I'll take them now.
Yeah, thanks, Quinn, for that talk. So I'm not sure if you're able to see the chat window, but we do have one question. So somebody was wondering, I think there's been some issues with KC-46 and the fuel leaks. Is that like another example of something that this ART process probably helped reveal a little bit sooner? Yeah, so the fuel leaks were actually found during operational testing and using ART. During DT, I'm an operational tester, obviously, but so I don't have a ton of insight into what was going on. But from my knowledge, the maintenance data on the KC-46 during DT was very limited due to that firm fixed price contract. And so by us performing ART and getting there early with our OT, that's when we really got our first in-depth maintenance data that was allowing us to find these fuel leaks. So there's another question, Quinn, if you can see it. So it says, do you think the pros of integrated testing, I'm sorry, I moved up. Do you think the pros of integrated testing will always outweigh the cons, or can some effectiveness suitability decisions be better supported by traditional testing? So just, preface this is my opinion. But I think in the historic testing, we get a lot away from capability. It kind of comes into this schedule thing, this cost thing. And I feel like we lose sight of the operators in a lot of ways. And to me, the biggest pro for ART is that it makes performance matter the most. And so traditional testing is great in a lot of aspects because, I've been frustrated so many times because the system isn't ready, or, kind of like I talked about with the communications is, Link 16 is a system that KC-135 tankers don't have. So if the Link 16 isn't working on a flight, is it because the aircrew didn't know? Is it because of the training, etc.? But I think overall, the focus on performance will make it outweigh traditional testing probably 9 times out of 10. And then it looks like one last question that we'll take. So somebody brings up the book Fate is the Hunter, has a great story about cargo loading in early World War II flight ops. It says, have you tried tabletop exercises to identify operational issues such as calculator before you have an aircraft? Sorry, let me just think about this real quick. I'm trying to wrap my brain around the question. And if you should be able to see it if you pull up the chat window. Yes, ma'am, I'm reading it. Cool. I would say, so a lot of the pre-planning that goes on, unfortunately, I was not around for. The testing on the KC-46 has been, I think the original IOT was planned for 2015 or 2016. So I'm not that aware of what type of tabletop exercises they've done then. I know we do interviews with operators. We talk to our pilots and our OT test pilots and booms all the time to have kind of what if exercises, but I don't know if there were any really, sat down, dedicated tabletop exercises. That's beyond me, unfortunately. All right. I think for sake of time, we will transition to our next speaker. So Lenny Lombardo currently serves as an analyst for RAMS, ILS Engineering, and the Analysis Division at the U.S. Army Aberdeen Test Center is our next speaker. At ATC, he serves as the lead analyst for both ballistic testing of helmets and fragmentation analysis. And previously, while on a developmental assignment at the U.S. Army Evaluation Center, he worked towards increasing the use of generalized linear models in ballistic limit testing. And since then, he has contributed towards the implementation of generalized linear models within the test center through test design and analysis. So Lenny, I will turn things over to you.
Okay, thank you, Rebecca. Is everybody able to see my screen?
Yes, we can see it.
Okay, great. Okay, my topic for today is the optimally based sequential test method for ballistic limit testing with a change in mechanism. All right, I'll just get started with a quick definition of ballistic limit testing. Involves shooting a kinetic energy threat at armor at varying velocities. We record the threat striking velocity and the penetration result, and then we attempt to model the probability of a penetration as a function of that threat velocity. So this information is used to evaluate both the system and can be inputs to models. Probability of penetration is typically assumed to be monotonically increasing with threat velocity. So basically at lower velocities, the round has less kinetic energy. It's less likely to penetrate the armor. At higher velocities, it has more kinetic energy and is more likely to penetrate the armor. But this isn't necessarily the case when there's a change in mechanism. So for a more complicated response, we need a more complex model. One such model is the Chang-Bode model, which is the focus of this talk. That brings us to the motivation of this work. So the current sequential test methods available aren't efficient. Chang and Bode recommended a modified up and down approach in a separate method recorded in top 10-2-218. They spend 80 shots over a velocity range below the V0 just to check to see if there's at least one complete over that range. And then after that, depending on the outcome of those first 80 shots, they use 60 shots using a modified Langley, or shots are taken at specified increments over a specified range. So basically they're spending 140 shots just to find a lower V50 value. So with all that said, I think these are pretty reasonable approaches given the complexity of the problem and the state of the art at the time they were developed, but I think we can do better. So for both body armor and vehicle armor testing, ATC has been using Nair's the optimal method. In test design, there's a lot of many different optimality criteria. The D-optimal method balances efficiently estimating both parameters of interest. So you have the V50, which is the velocity at which there's a 50% probability of penetration, and sigma, which represents the slope of the response curve. So this work focuses on applying the D-optimal approach to a more complex Chang-Bode model. All right, so what do I mean by a change in mechanism? So
Hey Lenny, I think you stopped sharing your screen.
yeah, it looks like I got cut off there. It looks like
Okay.
I've been able to hop back in.
All right.
Hopefully I can just pick up from where I was there.
Okay, yeah.
All right.
We're good.
Sorry
We can
about
see
that.
it now. No problem.
Okay, so diving right back in, a change in mechanism is when the threat-target interaction behavior changes over a given velocity range, such as probability of penetration is no longer monotonically increasing with increasing velocity. So shatter gap is probably the most commonly cited example. At low velocities, the threat stays intact. and the armor stops the threat. At intermediate velocities, the threat may stay intact but penetrate the armor, or it may shatter and not penetrate the armor. And at high velocities, the shattered threat has sufficient energy to penetrate through the armor. Okay, so here's kind of a comparison of response with a single mechanism versus response with two mechanisms. In both instances, we are modeling the probability of penetration as a function of velocity shown by those red lines on the screen. Individual data points are shown in blue. So for the response with a single mechanism on the left, probability of penetration is monotonically increasing. Basically, it just always increases with increasing velocity. But for the response with the two mechanisms, it increases, decreases, and then increases again. And then we want to show also point out that their data points are both circles and X's, and those are just denoting the two different mechanisms. So a couple of quick notes. Several methods have been proposed for modeling the change mechanism. So why choose the Chang-Bode model? This model makes more intuitive sense than, say, a higher order polynomial, and is more consistent with how we model a single mechanism. Chang-Bode model allows for a certain amount of complexity that is necessary to allow for different slopes of the two mechanisms compared to, say, a cubic fit. And the Chang-Bode model appears to give more conservative estimates for extreme quantiles than higher order polynomials or splines. Okay, so a couple of test considerations. Can the penetration mechanism be determined for each shot? So possible methods include both high-speed X-ray or post-shot X-rays. And if we can determine that mechanism, then we can use that information in analysis. Secondly, how much overlap is there between the mechanisms? So what do we mean by that? Is it easy to see just by looking at the completes and partials that there's two different mechanisms? So that would occur if there's not a lot of overlap. Or does it just look like one big mess of mixed results? So that would be a lot of overlap. So if there's a lot of overlap, then determining the mechanism for each shot is helpful and sometimes necessary. It can be easy to overfit a model. So typically we want physical evidence of a change mechanism instead of just relying on statistical methods such as information criteria. Lastly, if there's a lot of overlap, then it can be easy to miss the presence of one of the mechanisms in cases when you're not able to determine them. Lastly, if there is not a lot of overlap, so it's easy to determine which mechanism is which, then knowing the mechanism is still preferred but not as critical. And then finally, what if one of the outcomes is rare? So in the example given here, a threat tends to shatter before an intact threat would be likely to penetrate. So if it's like super rare that it can pretty much be ignored, then we can model that with a single mechanism. But in cases where it's maybe like a 10% chance or 20% chance of a penetration, so it's still relevant, knowing that mechanism is critical because it would be really easy to, in this case, miss the intact round mechanism. Let's see. Okay, it looks like. Oh, sorry, that's an old question. I'll keep moving then. So that brings us to the likelihood function for the Chang-Bode model. So why is the likelihood function improvement or important? Maximum likelihood techniques are used to iteratively determine our parameter estimates for our model. This work focuses on a d-optimal method for shot velocity selection. So a d-optimal method select points to maximize the determinant of an information matrix. Information matrix is the negative expectation of the second derivative of the log likelihood function. So the likelihood function provides a foundation for the test method and the analysis. So that's why it's important. There's a lot of information on the screen, but the main takeaway here is knowing the mechanism allows us to simplify the problem quite a bit. Okay, so what I mean by being able to simplify the problem, basically, if we know the mechanism, we can simplify it into 3 separate generalized linear models. So to be able to obtain unique estimates for our model, there needs to be a zone of mixed results. To that end, we use the initial design to get an overlap of partials and completes for our first mechanism, overlap of partials and completes for the second mechanism, and an overlap between the 2 mechanisms. So once we obtain the 3 zone of mixed results, unique parameters are determined. The next shot is the optimal point. So quick example of what all that means. So along the left axis, left y-axis is the probability of penetration. In blue, all these, we have our individual points. Circles represent our first mechanism. The X's represent the second mechanism. The zeros along the bottom x-axis are partials. All these ones are completes. And then we have the response curve based on the Chang-Bode model. In blue here is this line. And then along the right axis is the determinant of the information matrix. And then as a function of the next velocity. So this helps us choose the next velocity simply by picking off the peak of this orange curve. So our next shot in this case would be 255 meters per second. So shown here we have 4 peaks, but there can be up to 6. All right, so to evaluate the performance of this new test method, a simulation study was conducted. We used 4 true sets. In this case, the mu's for the 2 different mechanisms are symmetric about the mu for the mechanism probability function. And we explored deltas varying from 1 to 4. The underlying scale parameters are all equal. So all these sigma values are equal. And then the probabilities, P sub 1, P2, and P sub m all followed a logistic distribution. Initial guesses are exact, and we explored sample sizes varying from 40 to 100 in increments of 20. All right, so the first evaluation metric that we're interested in is the parameter median bias. So we have 6 parameters. We have a mu and sigma for each of those 3 probability equations, P1, P2, and P sub m for those 3 generalized linear models that I mentioned earlier. So the first thing we want to notice is that the mu's are this blue, red, and green, and all of those have negligible relative median bias. And that should come as no surprise because it's a balanced design, so we wouldn't expect any bias there. And then next is sigma. We do see a considerable amount of small sample bias with these sigma values in the lighter green, purple, and orange. This also comes as no surprise because the small sample bias for sigma is well known for generalized linear models. And we see as expected as sample size increases, that bias goes to 0. Lastly, as delta decreases, so going from 4 down to 1, we also see the median bias for sigma decrease. So consider a low velocity partial for the first mechanism. This point provides some info for P1, but little info for PM and no info for P2. So as delta becomes smaller, those shots tend to provide more information to the other curves. Those still separated by a mechanism. So the first mechanism shots really don't affect the second mechanism parameter estimates. All right, so moving on to the
Hey,
next,
Lenny, there was a quick question. Somebody was asking what the relationship between the mu, the sigma, and the P was.
Okay, thank you. Yeah, that's a great question. So I probably didn't explain that too well. I can skip back and just look at it real quick. All right, so these top three equations are the three generalized linear models, basically. And then each of these have model parameters, which are mu and sigma. So if you think about so in this case, we use the logistic distribution, but if you're familiar with the normal distribution, your two parameters are mu and sigma, and it's basically the same idea. So you have three generalized linear models. Each of those has mu and sigma as their parameter estimates of interest. Hopefully that satisfactory answers the question. Okay. So we're also interested in the root mean squared error. As expected, as your sample size increases, your root mean squared error decreases. Again, as delta decreases, the shots provide more information to the P sub M generalized linear model. So you see a decrease in the root mean squared error for both mu and sigma. So let's try to pick those off of the graph. So this lighter green, we see that when delta is big, this light green's up here. When delta gets small, it's down here. And that's kind of the same for this darker green. So this darker green's the mu. So it's up here and then comes down here. So all right, so for when the mechanism isn't known, then we use this, the likelihood based on the margin here. So basically the takeaway from this one is as trying to maximize the log likelihood function down here becomes a nonlinear optimization problem. So that's why knowing the mechanism makes it a lot easier. So unless the range had planned to collect information and determine the mechanism for each shot, this is the situation we would find ourselves in. Okay, so in situations when there's a little overlap between the two mechanisms, this unknown mechanism approximates that. As before, initial design is used to achieve overlap of the data. And we don't know the mechanism, so instead we achieve three regions of overlap in partials and completes to approximate the no mechanism result. And a couple quick notes here. This is a more challenging optimization problem than earlier. So a method was used to quickly assess the initial guess so that basically we don't have to wait very long between shots. Also implemented some algorithms to try to resolve a lot of convergence issues, but sometimes we still had a convergence problems. For these simulation studies, I think I ran 1,000 simulations for each of the conditions. So running that many, you can run into some weird situations. So as a catch-all, the optimal points were based on a cubic fit when the convergence failed. However, when we did get convergence, the optimal methods or the optimal points based on the Chang-Boat model were used. So this approach is not recommended when there's a lot of overlap between the two mechanisms or when one of the outcomes is rare, as we previously discussed. Okay, so here's an example, this time with the unknown mechanism. Along the left axis, again, is probability of penetration. This time, our data points in blue are only circles because we all know the difference between the two mechanisms. And then our curve, again, is a response curve based on the Chang-Boat model. Along the right axis, again, is determinant of the information matrix in orange. So In this case, that's as a function of the next velocity. So again, we pick off which ever of these peaks are highest. And if we look at the data, we see that the lowest velocity wound up being a complete. So the algorithm correctly picks a low velocity of 139 meters per second as our next target shot velocity. All right, so again, we did a simulation study just to see how this method performed. This time we varied between delta from 3 to 5 instead of 1 to 4 because those instances where there's a lot of overlap, we don't recommend this method for those not knowing the mechanism. So everything else is similar to the previous simulation study. All these P1, P2, and P sub M all followed a logistic distribution. All of our initial guesses for the 3 mu's and the 3 sigmas were exact. And again, we're looking at varying sample sizes from 40 to 100. And we see, again, relatively negative bias for mu. And again, sigma's bias and that sigma bias decreases with increasing sample size and decreasing delta. We see that help improve the sigma for the mechanism generalized linear model, or the mechanism sigma. All right, finally, for the root mean squared error, we see 2 competing observations. So as delta decreases, the root mean square error for sigma decreases. So it's this purple, orange, and lighter green. So they're way up here. And as delta decreases, those decrease. So that's kind of expected. Again, we're getting more information to the other areas as that delta decreases. So when you're saying knowing the mechanism, you're referring to 2 separate projectile types or a single projector type that it has a probability of shattering. Okay, so it's a good question. So when I say 2 different mechanisms, it's the same projectile, and that in the case of shatter gap, the projectile might shatter. So if you have like an armor piercing round, a lot of times we try to use a hardened armor, and we're actually attempting to shatter that round in order to defeat it. Lower velocities, that round might not shatter, so that's kind of where we get the shatter gap issue. Okay, one more note from this graph is the darker green, the mu sub m. When there's a large delta, we see that this is relatively low root mean squared errors compared to when, so I guess eyeballing this might be 0.38 for the 40 sample size versus 0.44-ish for the lower delta value. And so basically, without knowing the mechanism for each shot, it's difficult to estimate the mu for the mechanism, or the mechanism mu, when there's a lot of overlap. So as delta decreases, the data just looks like one big zone of mixed results. Okay, so a couple conclusions. We need a more complicated model. In this case, we use the Chang-Bode model for modeling when there's a change in the penetration mechanism. The optimal sequential shot selection method was presented. Cases both when we knew the mechanism and when we don't know the mechanism. And generally, knowing the mechanism is preferred. All right, so some future work, what I'm interested in now is developing likelihood-based confidence intervals in cases where the mechanism is known. So that's, if we look at the graph on the left here, we see circles and X's, so we know the mechanism. And these, the solid orange line is our response curve, and these dashed type lines are our confidence intervals around our response curves. So these type of confidence intervals relies on nested models. It's basically an inverted likelihood ratio test, but properties of chi-squared distribution may be used to combine all these and solve for these confidence intervals. Shown on the right here is an overlay of a normal approximation in green, so these green dotted lines. And so we see good agreement when we would expect a normal approximation to be good. I'm not too confident we could do it in cases where we don't know the mechanism, just because we want to be able to take advantage of that chi-square distribution. There might also be problems with local maxima that would make it difficult to calculate these. These do, using the Chang-Bode model, seems to outperform spline approaches to confidence intervals I've seen. Much tighter confidence intervals for the comparisons that I've been able to do. So with that, I'd like to take any other questions. Thank you very much for those who've already asked them. I'm sorry, go ahead.
Thanks. No, I was gonna say thanks, Lenny. Yeah, we'll take a minute or two to see if anybody has questions that they want to type in.
Okay, so can you explain how root mean squared error is smaller with smaller sample size? Tells two mechanisms. So I guess let me go back here. So can you explain root mean squared error is smaller with smaller sample size? So I guess as your sample size increases for a given delta, all these root mean square errors also decrease. And then any, let's see how that compares to the other one. I don't think they're on the same scale. Yeah, they're not really on the same scale, so it might be harder to compare. But generally speaking, if you know if you know the mechanism, then there's less uncertainty. You should be able to estimate the parameters better. Hopefully that answers your question. And the CB seem to outperform splines when the mechanism is unknown. So yeah, I'm sorry if I wasn't clear. These are only developed it so far for the case where a mechanism is known. I'm not convinced I can come up with a likelihood based confidence interval when the mechanism is unknown. So again, it's based on nested models. And if we went all the way back, we'd see that we don't really have nested models. It's kind of constructed differently, the case where the mechanism isn't known. So we wouldn't be able to take advantage of being able just to add up those chi-squared distributions to combine them to even calculate them. I don't know how I would do it for a case where I don't know the mechanism. So if I consider a nested logit structure when the mechanism is not known, I'd probably like to talk to you more offline about that. That would be great if you could give me some more information as to what you mean by that.
All right, thanks, Lenny. And yes, we can connect you with Jay Dennis to discuss that further. We'll move to our third and final speaker for today, Elliot Bartis. So Elliot is a research staff member at the Institute for Defense Analyses, where he works on test and evaluation of undersea warfare systems such as torpedoes and torpedo countermeasures. Prior to joining IDA, Elliot got his PhD in material science and engineering from the University of Maryland. And he was introduced to model validation through his work on torpedo simulation, on the torpedo simulation called the Centric Weapons Analysis Facility, or the ECWAF, which we'll hear more about today. And in 2019, Elliot and a few others were involved in the MK-48 torpedo program, which received a Special Achievement Award from the International Test and Evaluation Association, in part for their work on the simulation. So Elliot, I will turn things over to you.
All right, thank you. So thanks for the introduction. Good afternoon, everyone. I'm excited to share with you a case study of model validation done well. So this simulation is called the Environment-Centric Weapons Analysis Facility, or ECWAF. It's located at the Naval Undersea Warfare Center in Newport, Rhode Island, and it really has the potential to change the way that we do operational testing of torpedoes. And just before I go on, I have to acknowledge that what I'm sharing today is a result of a very nice collaboration between myself and DOT&E, and of course the very talented engineers, scientists, and analysts at NUIC, or the Naval Undersea Warfare Center, and also the Navy's test agency, COMOPTA 4. So just big picture, if we have reliable M&S, we can really change the way that DoD does business. M&S is a lot cheaper than in-water events or than any live event, and it can really give us new insights into how to prepare for war and learn about how our weapon systems work under conditions that we could never test in a live event. And so if you look at this map here, this is kind of describes how it works with torpedoes. We do live testing of torpedoes in those blue circled areas. So off the coast of Hawaii, off the West Coast, and off the East Coast. And whatever the performance is there, we kind of generalize to how that might be in potential warfighting areas, such as those shown in those red boxes there. We could never test in the red boxes just for logistical reasons and maybe even diplomatic reasons, but they're the perfect areas that for us to model. But if we're going to use this model to make, or any model to make pretty important decisions, we have to be able to trust it. And the process of establishing that trust is validation. And that's where we compare a model's predicted results to actual outcomes. And ideally, we can quantify the difference and really get a nice understanding of how accurate a model reflects reality. So IDA has actually released Best Practices Handbook on how to do model validation using statistical techniques. And so researchers like me can apply that handbook's general guidance to the needs of specific programs. So, and after this handbook is published, we plan to put together a series of case studies of programs that are doing model validation, so as a reference and as a good example of how to do it well. So the Mark 48 torpedo is shown on the top. That's what I'll be talking about today. But there are other programs as well whose operational testing plans to have M&S in it. And so there's the air-to-air missiles like the AIM-9X and AIM-120 AMRAAM, and also the Patriot missile. But in addition, in a non-explosive way, the CVN-78's operational testing plans to model the sortie generation rate. So if you're interested in any of these, keep your eyes peeled down the line. One very appealing factor or one very appealing aspect of M&S is that you can save a lot of money and of course learn potentially more than you ever could based on in-water testing alone. And so if we can validate the ECWAF, and that is an if because we're in the middle of it right now, we can potentially save a lot in resources. So what I show here on this plot is the cost of OT on the left axis for 3 different torpedo variants. APB 4, 5, and 6 are just different software and hardware configurations. The blue data shows the approximate cost for an in-water run, which I estimated about $200,000 per run. And the orange data is the M&S, which is about $200 per run, so a lot less. And if you look at APB 4 and 5, you see that both of them have in-water operational testing exceeding $25 million. And if you squint your eyes for APB 4, you can just make out a sliver of M&S done there. In APB 5, we dramatically increased the amount of M&S we're doing. But we have to have a large amount of M&S and in-water data because APB 5 is where the validation is occurring. The payoff comes down the line with APB 6. And that's where, again, if we can validate, we plan to reduce the number of in-water firings by more than half. And we're really shifting the statistical burden of OT to the simulation. I like to point out, though, that we could never completely get rid of the in-water events, no matter how good the simulation is, because there are certain things that you learn from in-water events that you could never learn in testing. And but what we can do now is focus our resources on areas where, say, we don't trust the simulation as much, or scenarios that we know have been historically challenging for the torpedo. So just a little background on torpedoes. It's the submarine's primary weapon to take out other submarines and surface ships. And every so often, the Navy releases a new variant of the torpedo, whether it's hardware or a software upgrade, and we have to test it before it's fielded. And of course, because we have to test it, we encounter the usual obstacles that weapon systems have. Testing is, of course, expensive. Safety is always paramount in testing, and so we can't do everything we want. But one thing that's extremely difficult, I think, for our community is the time it takes to do it. There are a limited number of attack submarines out there, and to schedule 2 of them to appear in the same body of water at the same time is a huge challenge, and it's only going to get more difficult. But these are obstacles that M&S can overcome. So this is what the ECUF looks like. It's a hardware in the loop model. On the top of that bench are 3 torpedo, sort of the brain part of the torpedo. That's where the sonar signal processing is and the tactical software. And below the bench is the computers that make up the actual simulation. So they're connected to it by a series of cables. You can kind of imagine it's like putting the torpedo in the Matrix, like in the movie. And the simulation has to model the environment, the targets in it, and how they move, and also how the torpedo moves and the sound that it puts into the water. It's an extremely complex simulation. And one key upgrade to this simulation is that it is now environment-centric. It's been around since the 90s, but it wasn't always an environment-centric simulation. And so we know from historical testing that environmental factors play a big role in how well the torpedo performs, but they are notoriously hard to model. So if you just compare these 2 situations here, on the left we have a rocky littoral environment, and on the right we have the open ocean. So imagine that you're a torpedo and you're using your sonar to find a target. On the left, it's a pretty complex environment. You have potentially big boulders that might look like a submarine. You have, every time the torpedo activates its sonar to try and find the target, that acoustic energy reflects off the bottom and comes back to the torpedo. And it's just a lot of extra signal that the torpedo has to deal with. And so you have to model that complexity accurately. Open ocean is very different. It's a much simpler environment. If the torpedo sees something, it's most likely going to be the target. So it's easier to model. It's also just easier for the torpedo as well. So focusing in on the validation itself, we're in the middle of it right now, and I think it's been very successful. And there are many reasons for that, but I've distilled it down to 6. The first is that there's been a strong Navy and OSD investment in the ECUF's development and the VVNA. It was never a last-minute decision to make the ECUF environment-centric. This was, I think, started about a decade ago, upgrading the computer hardware to make the ECUF more trustworthy. And we know that we're not getting the payoff until the next variant. So again, there was a lot of foresight in this whole process. The second one is that the Navy brought DOT&E and IDA in early. Pretty much day 1 with the accreditation plan, we were providing helpful suggestions and making sure that, if this is going to be used in OT, that we're following DOT&E's guidance. The third one is, I think, unique to the torpedo community, and that's that we have a lot of in-water data in the Navy's historical database. The Navy regularly shoots about 200 torpedoes a year in their regularly scheduled submarine command course. So that's where a prospective commanding officer trains to become a commanding officer. And so not all of that data is operationally representative, but there is some of it that we can use. And the more in-water or live data you have to do your validation, the better. The fourth one here is cultural, and I can't emphasize it enough. Having frequent working level meetings, for us, it's at least once a month, and sometimes there's been periods where we've met once a week. And just overall open lines of communication between all the stakeholders has been very helpful. It's a very collaborative culture we have. Everyone's on the same team, and I really have no hesitation about picking up the phone and calling an analyst either at ComOpta 4 or at NUIC to brainstorm a solution to a concern that we have. The fifth one is that the ECUF developers and torpedo developers work side by side at Newark. So this means that we don't have any integration issues. As they're developing the torpedo, they're integrating it into the ECUF, or maybe just the WAF or the old version, to test it out. And I think that's different from other models where, say, a radar model, a missile model, and a combat system model are all developed at different locations, and you bring them together and they don't talk to each other. So we don't have to deal with that. It's a very torpedo-focused simulation. The last one is that we have clear intended uses. There's two parts to that. First, it's plural. There's more than one intended use. And the second part is that they're clearly written. And I'll overview those intended uses in an upcoming slide. When we're talking about torpedoes, the most important metric is torpedo effectiveness, and that's how we describe its performance. It's the probability of the torpedo intercepting its target if it's given an opportunity to do so. So if the crew fires a torpedo way out in left field, and it never has a chance to see the target, we're not going to attribute that to the torpedo's effectiveness. One important aspect of torpedo effectiveness is that it's a function. It's not a single number. It's a probability that depends on the details of the scenario, like how your target's evading, and of course, those environmental parameters. And you'll see in an upcoming slide that our goal is to develop that torpedo effectiveness function. So day one, you put together your accreditation plan, and one of the first steps is coming up with your intended uses. For us, for the ECUF, we have 5 intended uses, and they take a crawl, walk, run approach. So the first one listed here is the easiest to achieve, and the 5th one is the hardest to achieve, but also the one that has the highest reward. The first one is to use the ECUF's predictions to run side-by-side comparisons of torpedo variants. So what we're asking here is the new torpedo at least as good as the old one, given the same initial conditions? And that's something that we've already been accredited for in the past. So at a minimum, we're going to re-accredit for a historical accreditation. As you go to the next intended uses, they get a little harder to get to. And the 5th one is the holy grail. That's using the ECUF to predict torpedo effectiveness and using that prediction in the test report. So intended use 5 is what we all want to get to, but if we only had that one, we'd be taking an all or nothing approach to the validation. By having multiple intended uses, we make sure that we get something along the way. So the approach we're taking in this validation is a machine learning approach or a statistical learning approach. And we're validating the ECUF in the general case rather than only specific cases. If we were doing it in only specific cases, we'd have to press the I believe button for everywhere else. But what we're doing is kind of validating everywhere. And there's 3 steps to this. The first one is to do your ECUF runs. And so we get together and we generate our designed experiments. And what we get is the experts at Newark, they run the simulation, and they give us a really nice tidy table afterwards. And and what the data looks like is a series of conditions that leads to a hit or a miss. In the second step, we create our predictive emulator. So that's another term for this is a meta model. It's a mathematical model that describes the computer model. And this is pretty much the T effectiveness function. So we use statistical techniques like logistic regression to build this emulator. And what we get is we don't get a hit or a miss out of it, we get a probability of a hit. The third step is where the validation occurs. And that's where we take conditions from actual in-water events and plug them into the emulator. And what we get is a prediction that we can compare with the actual outcome. And I'm going to share with you just a handful of the validation metrics that we're looking at. So for those of you with a machine learning background, this is sort of like cross-validation. Our ECUF simulations are the training set, and our in-water runs are the test set. We're also doing this in one of the I think keys to success here is that we did this in a 2-phased approach. So that really overall reduced risk and gave us an opportunity to learn. The first phase I look at as a rehearsal of that 3-step process. And with it, in this phase, we used existing data with the historical torpedo. The Navy has a very well-organized torpedo database, and we can use those historical runs to do a dress rehearsal of the validation. So we're not asking for any new data, any new in-water data, just simulated data. There is a limitation here, which is that historical data doesn't quite span the operational space as much as we'd like, but it's a rehearsal. And one of the 2 main outputs here are factor screening and lessons learned, which we implemented before going to the second phase. which is the same three-step process, but with the new system. This is the torpedo that's currently under test. The biggest difference here is that the in-water test was, we used design of experiments for the in-water test, so it spans the operational space better than the data in phase 1. So there's a lot of statistical design here, both for in-water and the ECWAF. And I'm going to share with you just the how large the operational space is for the ECWAF. One of the first steps in DOE, design of experiments, is to identify your response variables, or what I call these important outcomes here. The T effectiveness and what the sailor cares about is hit or miss. But we want to make sure we're hitting and missing for the right reasons. So we look at secondary outcomes like the false alarm rates and the acquisition ranges. And then we identify the factors that impact those outcomes. So evasion tactic, target type, and the exact details of the environment we're in. So for the simulation, we actually have 14 factors. So it's quite a large operational space we're talking about here. So we have our factors on our DOE. The Navy, the analysts at Newark, they run the simulation and we get the data, we do logistic regression, and then comes the validation. And I'm going to share with you the metrics some of the metrics that we used. And there are many that exist, but I'm just going to share 4 of them. So at a very high level, we have accuracy. Just how often is a prediction correct? You have to know this. But there are other measures of goodness, like specificity, which asks how often a miss is predicted correctly. And that gets at what statisticians call type 1 errors or false positives. So this, on the lower left, this doctor, his pregnancy test has low specificity, telling this gentleman that he's pregnant. There's a similar metric called sensitivity, which is how often a hit is predicted correctly. And this gets at what statisticians call type 2 errors or false negatives. So this doctor on the right, her pregnancy test has low sensitivity, telling this woman that we can all tell is pregnant that she's not pregnant. So how'd we do in phase 1? I think the results were quite promising, but there was a limitation there. So overall, the accuracy was high. 71% of the time, the prediction was correct. The specificity was 32%, which left something to be desired there. It looks like the ECWAF is over-predicting performance. Now, I think that there are some very good reasons that this number should be higher that I'm not going to get into in this brief. For sensitivity, it was quite high at 83%. So if a hit occurred in water, it was likely to predict it. Now, one thing I want to say here is that I don't expect any of these numbers to ever be 100%. These are probabilities, and if there's a 30% chance of a torpedo hitting, it's not, we would predict a miss, but there's still a 30% chance of a hit. So we'd never expect these to be perfect. One thing about these metrics is that they're kind of yes or no. We're in a yes/no world here. Does it match or does it not match? But if you've been to other DataWorks talks or taken DOE courses, you know that continuous metrics have more information. And so we didn't want to reinvent the wheel, and so we asked what kind of communities are asking similar questions. And one community is meteorology. They make a lot of predictions. And so just imagine you have your 2 weather apps, weather.com and Weather Underground. And one says there's a 51% chance of rain tomorrow, and the other says there's a 95% chance of rain tomorrow. Well, you're not going to be stuck in the rain without an umbrella. So, but both of them are saying that it's going to rain. So the next day when you go to lunch, you bring your umbrella and your rain gear. It starts raining, and both models were correct, but I mean, one predicted 51% chance of rain. So it was somehow less correct, right? So meteorologists have a metric they use. It's called the Brier score. And what it does is measure the accuracy of probabilistic predictions, like probability of rain tomorrow or probability of a torpedo hitting, and rewards a prediction that's closer to the outcome. So I show in this example here, there's 2 scenarios. Let's say that our meta model predicted a 50% chance of a hit in one and a 90% chance of hit in another. I'd call anything 50% or higher a hit. And in both cases, there was a hit. In the Brier score, it's a pretty simple calculation. It's just the difference between the prediction and the outcome squared. And you can see that as you get closer to your outcome, your Brier score goes down. And I looked at the median Brier score in that first phase, and it was quite low at 0.07, another good sign. I took the Brier score I looked at the Brier score a little deeper and saw that when the ECWAF made an incorrect prediction, it wasn't clustered in a particular area or scenario. And that was really helpful because it was the data showed that we should go to that second phase. So if you look at this chart here, this is the distribution of Brier scores. And you can see that, sure enough, most of them are below 0.1. Great to see. But there's some in this red box here where the Brier score is 0.5 and higher. And these correspond to predictions that are off by 70% or more. So again, it's okay for a prediction to be off, but I was checking to see if these sort of grossly incorrect predictions had anything in common, and they didn't. And that was great to see, because if they did have something in common, I would tell the Navy, you know, hey, this is something that we should fix before we go to the second phase. I didn't see it, so we moved forward. And we had an opportunity to make some changes because of this two-phase approach. And one of the changes we made was moving from a factor screening design in phase 1 and to a space filling design in phase 2. So this applies to continuous factors only. For a factor screening design or a central composite design, you have your operational space is still just as large, but you're focusing your test points at the boundaries with some center points. In phase 2, in that space filling design, you really fill in the interior. And we would only have done this because of that first phase using the factor screening design. Second phase, we have, I think, better predictive power here. Another change we made was that we went from one big design in phase 1 to 3 designs. So we have 400 deep water simulations, a much larger number of shallow water simulations, and then a pretty small design of threat models and in threat environments. And so this is actually a very efficient use of our resources, because shallow water is hard to model, and it's also hard for the torpedo. So we're really narrowing in on where we can learn the most. So this is the last slide of my talk here. The way I envision this ECOF emulator is one that will evolve and constantly improve. I talked about how the ECOF data is the training set, but after we validate, we can add all historical data into that training set and make new predictions. And then as new torpedo variants come in, the model can continue to learn from that and become more and more. So that's what I prepared for today. Thanks for everyone's attention, and happy to take any questions.
Thanks, Elliot. If you're able to see the chat, we do have one question so far. And that was a question about, are there factors that you had to leave out of the model, whether that be due to cost or inability to model them, that you know do play a role in the real world? And is there a way that we can try to attempt to account for them?
So, I mean, there are absolutely things that you cannot model. Sometimes in an in-water torpedo event, the torpedo goes off into left field and we don't really know why. There's maybe a school of fish out there that we could never model. So we tried our best to, I mean, we have 14 factors, so it's quite a large operational space, and I can't think of any factors that would have had a huge impact that we're not considering. And I think there are a lot of ECOF analysts on this call, so if they have any insight on that, recommend they jump into the chat.
And then there was another question somebody asked about, so is miss distance something that you guys have considered instead of hit miss? Would that be informative?
That's a great question, because continuous metrics are best. So for some fixed C, the miss distance less than C. So the torpedo it's really an autonomous vehicle. So if it misses, it can turn around and find the target again. So in addition to that, it has to be close enough. I guess that's what Melissa means by fixed distance C. It has to be close enough to fuse. And there is a lot to learn there, but typically with the torpedo, I think if it's close enough to a target, there are very few near misses. It's mostly, you know, if it's not going to hit the target, it's during the search phase typically. It's because it can't find it initially, or if it gets really close, I mean, it's pretty reliably, I think, going to be successful.
Elliot, looks like you have one more question there, yeah.
I don't know what data probe is. And so warhead lethality is pretty separate from what we do here. And I think, yeah, the air-to-air missile, or an air missile, I think it's, in terms of miss distance, it's a little bit different, because I don't know much about missiles, but I don't think it's necessarily going to turn around and be successful. The torpedo it's a lot faster than its target. So, I mean, if it has a near miss, it's going to, even if it has a near miss, it has the opportunity to have a second, third, or I mean, even fourth attempt. Okay, Melissa Surso, she's one of the brilliant analysts at Newark working on the WAF, and so she has some answers there, it looks like. And then John Castano. Oh, that's a private message. I'll link up with him afterward.
All right, thanks everybody again for attending. With that, I'm going to end the session. So thanks again to all of our speakers for giving us another great set of talks.